everyone, welcome back to Let's Week's Algebraic Graph Theory seminar. Let's week, Alena Ernst. She's going to talk about intersection theorems for finite general linear groups.
Yeah, thanks. So this talk is about a joint work with my PhD supervisor, Kai Schmidt. And I would like to start straight out with the classical intersecting sets, so with the Erdős-Corrado theorems, which is in a setting of sets. So here we see 4 points, which are indicated by 4 colors, and are interested in finding a family of 2 sets such that any 2 of these 2 sets have non-empty intersection. So what we could have taken, for example, is this family here, or the trivial one, which would be given by the family consisting of all 2 sets that intersect on the same point. And the question is, how large can such a family be? So for arbitrary t-intersecting sets, the answer was given by Wilson, namely for n sufficiently large compared to k and t, a t-intersecting family of k sets has size at most this binomial coefficient that you see here, and if equality holds, then all members of the family contain a fixed t subset. Okay, but how would one attack to prove such kind of a theorem? So let us first of all focus on the one intersecting sets. There are several proofs, but we want to stick with the idea to construct a graph such that our one intersecting set is an independent set within the graph. And then we want to apply the classical HOFFMAN bound, which gives us an upper bound on the size of independent set in terms of the minimal eigenvalue, and also characterizes the extremal case. So for this example from the previous slide, we can, for example, take this, or we do take this graph up here. So the vertices are given by all 2 sets of this 4 set, and we have an edge between 2 sets whenever the intersection is empty. So it's described by the adjacency matrix that you see below the graph. Calculating the minimal eigenvalue gives us -1, and applying the HOFFMAN bound then gives us our desired upper bound for the size of one intersecting family of 2 sets. Okay, for attacking the proof of t-intersecting family of k-sets, so for k-sets, so for the upper bound, we want to again construct a graph. So we will not stick with the proof of Wilson, but we want to construct again a graph such that our independent set is such that our t-intersecting set is an independent set. And for that, we will take the definition or the notion of an association scheme. What is an association scheme? Well, basically we think about a complete graph like this one, and then we color its edges. So we get some adjacency matrices, and together with the identity matrix, we see the following property, namely taking the product of any 2 of these adjacency matrices. They are again a linear combination of these 3 matrices that we have just taken. And in addition to that, any product of 2 matrices commute. So this gives us an association scheme. So in general, just think about a complete graph with vertex at x. We color its edges with k colors, get some corresponding adjacency matrices, and they, together with the identity matrix, then define an association scheme if the span of this set is a commutative matrix algebra. And they come with a nice property because all of these adjacency matrices, so together with the identity, have k+1 maximum common eigenspaces. And during this talk, they will be denoted by this capital V. Okay. And the association scheme that you see here on the top of the slide is a special one because it is indeed the Johnson scheme. So for general k and n, the vertices are just given by the set of by all k sets of n, and the adjacency matrices are given by the following that you see here. So we take the intersection of 2 k sets. So this gives us an association scheme, and we can even write these their eigenvalues down. So for different j, we get the eigenvalues pij corresponding to the adjacency matrix AI. Okay, so as I mentioned, we want to construct a graph such that our t-intersecting set is an independent set within the graph. And then we will not apply the classical HOFFMAN bound, but a weighted version, which is the following one. Okay, so in terms of association schemes, we just think about an association scheme on the vertex at x, and together with the common eigenspaces, Vi. And then now we take a weighted linear combination of these adjacency matrices, but just over some of these adjacency matrices. We do not have to take all of them. Then this theorem gives us, in fact, an upper bound on the size of an independent set in terms of the minimal eigenvalue of this weighted linear combination. And it also characterizes the extremal case, namely, if equality holds, then the characteristic vector of this independent set lies in the eigenspaces corresponding, or in the sum of the eigenspaces corresponding to the trivial one or the minimal eigenvalue. Okay. Yeah, so how do we apply this theorem? The association scheme that we will take will be the Johnson scheme from the slide before. But since we need the eigenvalues, or at least the minimal eigenvalue of the weighted linear combination, let us first take a look on how these eigenvalues then look like. Well, due to the fact that all the adjacency matrices have these common eigenspaces, the eigenvalues of the linear combination is just the weighted linear combination of the eigenvalues of the AI. Okay. So, and in the setting, we now just take omega I to be the following. So you see a quotient. And for all of these who are familiar with association schemes, the VIs are the valency of the Johnson scheme. The Z is a T-Steiner system, and the BI are is the corresponding inner distribution. So we can write these things down explicitly. They are something like this. You don't have to recall how they exactly look like, but just taking such an omega I, they fulfill the following condition, at least for n-sufficiently large. So we know how the minimal eigenvalue looks like. It looks like this. So in terms of the size of the T-Steiner system. And then applying the weighted HOFFMAN bound onto this, we get our desired upper bound. So what you should take from this slide is basically in the set case, so speaking of intersecting family of sets or of t-intersecting family of sets, we can write the weights omega I down explicitly. And applying the weighted HOFFMAN bound then leads us to our desired upper bound. Okay. So this is the set case, but intersecting sets can not only be found in sets, but also in the symmetric group, for example. But what is an intersecting set of permutations? So for this, let us continue with an example. So here, this picture has to be understood as follows. Namely, each of these rows, so row 2 to 5, give us a permutation of the symmetric group on 5 elements, which are here indicated by these 5 colors. So this row here, for example, gives us the identity permutation. This row up here is light blue is mapped to blue, green to light blue, and so on. And what we observe here is now, taking 2 of these permutations, we find one color on which they're equal. So in this case, green is mapped to light blue, and that applies to both of these permutations. And proceeding in this manner, we will always find one color on which they're equal, which gives us an intersecting set in the symmetric group of 5 elements. A trivial example would be given by a subset, which is equal always on the same color. So in this case, on light blue. Okay. And it is a special one because it is a subset of the stabilizer of one point, and indeed a coset of the stabilizer of an element. So any coset is in fact intersecting, and its size is given by n-1 factorial. And they play a special role because it was proved that the size of an intersecting set in a symmetric group is in fact bounded by the size of the stabilizer of a point. Yes, and the characterization of an extremal case took a little bit longer to prove, but it was in fact proven as well that an intersecting set in the symmetric group of maximal size is a coset of the stabilizer of a point. Okay, which now leads us to a strength aversion, or we cannot only ask for intersection at all, but for a t-intersection. So what is the t-intersecting set? Now taking 2 permutations of the subset, we now find at least 2 colors on which they're equal. So in this case, both permutations are equal on blue and orange. Or proceeding in this manner, we would always find 2 colors on which they're equal, which gives us a t-intersecting set. So in general, a subset of the symmetric group is t-intersecting if taking any 2 of these permutations of the subset, we find t colors on which they're equal. Okay, and in the following, I would call any coset of the stabilizer of t distinct elements a t coset, and they give us the trivial examples, namely any t coset is a t-intersecting set, and its size is given by n-t factorial. Now, knowing the result for the one-intersecting sets may raise the question whether this gives us again an upper bound on the size of t-intersecting sets. Okay, and that was conjectured by Deza and Frankel, namely whenever n is sufficiently large compared to t, then the t-intersecting set is bounded by the size of a t coset. And if equality holds, then this set is indeed equal to a t coset. And it was proved that this conjecture does hold. Okay. Now, losing this condition a little bit more leads us to more general question, namely to t set intersecting sets. So here, instead of being equal on points, we are just equal on sets. So taking two permutations of this set, we now find a two set on which they're equal. So here you see that the image of the two set consisting of green and pink is equal to green and orange, and that applies to both of these permutations. And proceeding in this manner, we will always find a two set on which these two permutations, so for any two permutations, we would find a two set on which they're equal, which gives us a two set intersecting set. So in general, a subset of the symmetric group is t set intersecting if for any two permutations of the subset, we find a t set on which they're equal. And again, a trivial example would be given by any coset of the stabilizer of a t set, which is indeed t set intersecting, and its size is given by the product that you see here. And the question that may arise again is whether this gives us, again, a size on the upper bound, an upper bound on the size of t set intersecting sets, and whether they are the only t set intersecting sets of maximal size. And this was, indeed, it holds at least if n is sufficiently large compared to t, and was proved by Alice. Okay. So how would we attack this problem now in order to prove it? So we again want to construct a graph. So at least for we just focus on the point intersecting case, not on the set intersecting case, but on the point intersecting case. And we want to construct a graph such that our t intersecting set is an independent set within the graph. Okay, so for the t equal 1 case, what we could do is we can just take the derangement graph as a possible way to attack this. So the vertices are given by the permutations of the symmetric group. Its adjacency matrix is given by the following. So the element in the adjacency matrix corresponding to pi and tau is equal to 1 whenever this quotient pi inverse tau is a derangement, which means that the permutation does not fix any point. So this graph is then regular, and the minimal eigenvalue is known. So applying the HOFFMAN bound then gives us the upper bound that we wanted to have. So that the one intersecting sets are bounded by n-1 factorial. Okay. But for t greater than 1, this approach doesn't work anymore. So what we want to do is, again, we want to apply the weighted version of the HOFFMAN bound, which, just as a recall, was the following here. But it was in the setting of association schemes. So first of all, we have to make sure which association scheme we should take. It will not be the Johnson scheme from the beginning, but we will take the so-called conjugacy class scheme, which indeed exists for any finite group G. So our complete graph now has the vertices being the elements of this group G. And the adjacency matrices are now given by the following. So the entry corresponding to GH is equal to 1 whenever the quotient G inverse H lies in the ith conjugacy class. So with Ci, I indicate the conjugacy class corresponding to I. Okay. And since we are working, since we are working with finite groups, we can make use of the representation theory. So taking the irreducible characters of the finite group, we can write the eigenvalues of AI down in the following way, where chi k is now the irreducible character evaluated on the conjugacy class I whenever there is an index I written in it. And it's complex conjugated, and this one here is just the degree of the irreducible character. Okay, so coming back to our symmetric group, we will indeed take G to be equal to the symmetric group. Then its adjacency matrices are given by the following, where now you see that I didn't put an integer here anymore, but a sigma, which is a partition, so a number partition of n. And that is due to the fact that the conjugacy classes and the irreducible characters of the symmetric group are indexed by a partition of n. So their eigenvalues are looking like this, where now you see that I omitted the complex conjugation because in the symmetric group, all irreducible characters are real valued. And yes, and it's evaluated on sigma, so lambda and sigma are now partitions of n. Okay. So for applying the weighted HOFFMAN bound, or the weighted version of the HOFFMAN bound, we have to make sure how our eigenvalues look like in order to calculate the minimal one. Okay. So just as a recall, how the eigenvalues then look like, they were just weighted linear combinations of the eigenvalues of the adjacency matrices. And since we now know how they look like, we can restate this. Okay, so now thinking about the second part of the statement, it was that having a t-intersecting set of maximal size, it is equal to a t-coset. So what we make sure is, applying the weighted HOFFMAN version of the HOFFMAN bound, is that we at least are contained in the right eigenspaces. And for this, we make use of the following, namely, the sum of certain eigenspaces, namely these lambda that are in some terms determined, are spanned by the characteristic vectors of t-cosets. So what we would just take is, we want to have that the minimal eigenvalue of our weighted linear combination is only applying or corresponding to these lambda that are appearing here in the sum, so that we make sure that at least our characteristic vector of the maximal t-intersecting set is contained in this vector space that is spanned by the characteristic vectors of t-cosets. So we know on which lambdas we want our minimal eigenvalue to appear. But we still have to make sure which conjugacy classes and thus which adjacency matrices we want to take, because recall, we wanted to have that our t-intersecting set is an independent set within our constructed graph. So we just will take conjugacy classes which have lower intersection. So let me explain what I mean by that. So for this, the conjugacy class of the symmetric group, an example. So here you see that the number of fixed points corresponds to the number of one cycles of these permutations. So translating this into the cycle type notation means we just have to count the number of ones occurring in the cycle type. So for example, taking now the orange mark conjugacy classes, give us some classes that do not fix a two tuple. Okay, and for arbitrary t, we could just take the conjugacy classes such that our first part has at least n minus t, and we are not equal to this one, which does fix a t tuple. But all of these conjugacy classes then do not fix a t tuple. So this will be the conjugacy class we want to take in our weighted linear combination. Okay, and now let us assume that we would get some weights omegas, so that we would get on these conjugacy class that we were just talking about some weights such that this is our minimal eigenvalue, and the minimal eigenvalue is only corresponding to certain lambdas that we were just talking about a few slides before. Then, well, since this will only apply for n sufficiently large, our weighted linear, our weighted HOFFMAN bound would give us our desired upper bound on the size of t-intersecting sets. And in the case of equality, we would also get that the characteristic vector is spanned by the characteristic vectors of t-cosets. So we would be done in this case, so at least for the upper bound. But how do you explain why these weights exist so that these conditions are fulfilled? Well, for this, we interpret this one as a system of linear equations. And the matrix we have to focus on is basically the one coming from the irreducible characters up here. So this is, so we have to take a look at the character table. So again, an example. This is a character table of the symmetric group of 5 elements. Each row gives us an irreducible character. And here we see the conjugacy classes corresponding to the different partitions. And we are basically interested in this little corner up here. So that one that is now marked in orange. And we have to argue in a way that taking a look at this 3 times 3 corner up here, our matrix is invertible. And then we would argue why omega is also a good choice for the last character that we would exclude, and we would be done. But now using the representation theory of the symmetric group actually would give us that so this is just the character table again with a matrix notation. And the representation theory now would give us that there exists an invertible matrix, indeed a lower unitriangular one, such that the product of these two matrices give us again an invertible matrix, that is the one down here. Okay, and now since we are only interested in this little 3×3 corner up here, we could explain that this was that this one is an invertible matrix because it is the product of two invertible ones. Okay, so this will give us then the ways that they exist, and we would be done. But in fact, I have to be honest, the proof of this upper bound is not as easy as I was just telling you. It is way more difficult. And the reason is, on the one hand, because when just taking the absolute values in this matrix here and comparing the first row, for example, with the last one, we see that they are equal. Or the second row and the second last one, we also see that they are equal in absolute value. So there's a lot of more work to be done in order to really get this the size of the upper bound. Okay, but I just let some matrices pop up magically. But what are these matrices? So what is this matrix and what is that one? So let me explain this in a very lightly. So we make use of the representation theory, and this comes basically from the Young's rule. So the matrix on the left-hand side that we just saw on the slide before corresponds to the Koska numbers, and the one on the right-hand side corresponds to a permutation character. So this is a matrix notation, and what is this character up here? So for this, let me recall what a mutabloid is by this picture. So we just take all tableaus where they have the same entries in each row. So we just compare the rows. If you're not familiar with mutabloids, just think about set partitions. Okay, and now this character xi up here is the permutation character on mutabloids, which is evaluated on a permutation of the symmetric group equal to, well, we just count the number of mutabloids that are fixed by this permutation pi. Okay. So that is the story behind the symmetric group. Okay. Well, now that we tackled the symmetric group, leads us to the next one, namely to a Q-analog setting. Oh, no, sorry. Oh, sorry. We are not done yet, because we've just found that the upper bound is that what we wanted to, but we applying the weighted Hoffman bound only gives us that for n sufficiently large compared to t, the characteristic vector of y is spanned by the characteristic vectors of t cosets. But we wanted to have that the intersecting set is indeed equal to a t coset. And in order to achieve this, there's a lot more work to be done. And it can be, for example, deduced by a result of Alice, which is a stability result. And applying this one would then also get that in the extremal case for n sufficiently large compared to t, our t-intersecting set is indeed equal to a t coset. So there's still a lot of more work behind it in order to get the extremal characterization. Okay, but now, since this was the part for the symmetric group, and this leads us to a Q-analog setting, namely to intersecting sets in the finite general linear group. But what is an intersecting set in the finite general linear group? So for this, again, an example, we focus on the finite vector space, which f2 to the power of 3, which should be spanned by the 3 basis vectors. And you see all 8 elements on the right-hand side, where the gray one, the gray dot here, should denote the all-zero vector. Okay, so again, an example. And now taking two matrices, so 2 rows, and comparing them, we find 4 colors on which they're equal, so which is equal to q to the power of 2 in this case. And thus this gives us a t-intersecting set of the finite general linear group. So in general, a subset of the finite general linear group is t-intersecting if taking any 2 matrices of the subset, we would find q to the power of t elements on which they're equal. And this example that you see here is again a special one, because it is a subset of the stabilizer of two linearly independent elements. Okay. And again, I will call any coset of the stabilizer of two linearly independent elements a t-coset. And they give us our trivial example here. So any t-coset is a t-intersecting set, and its size is given by the product that you see here. And now knowing the results for the symmetric group leads us to the question whether this gives us, again, an upper bound on the size of t-intersecting sets, and whether they are the only t-intersecting sets of maximal size. Okay, but before we answer this question in general, let us take a look at already known results. So for example, it is known that the size of a one intersecting set, so t equal to 1, in the finite general group is at most the size of a one coset. And for n equal to 2, it is known that the characteristic vector of a one intersecting set of maximal size is spanned by the characteristic vectors of one cosets. Okay, and we obtained the following result. Namely, having a t-intersecting set in the finite general group, and if n is sufficiently large compared to t, then the size of the set is bounded by the size of a t-coset. And in case of equality, the characteristic vector of y is spanned by the characteristic vectors of t-cosets. And here I would like to mention that this bound was in fact recently and independently obtained by Ellis, Kinner, and Lifshitz. And whereas we use techniques like the eigenvalue techniques and especially the representation theory of the finite general group, they use completely different ones. Okay. But are the t-cosets also the only t-intersecting sets of maximal size? So the question here is unfortunately no. And the reason is basically because having a t-intersecting set, then also the set consisting of all transpose matrices is t-intersecting. But what is known, for example, is having an intersecting set of the finite general group of 2 times 2 matrices of maximal size, then it is a one coset or the transpose of a one coset, which led us to the conjecture that having a t-intersecting set for arbitrary n of maximal size, then if n is sufficiently large compared to t, the set or the set consisting of all transpose matrices is a t-coset. And that was in fact proved also by Ellis, Kinner, and Lifshitz in the same paper where they proved the bound. And I will comment on this later on. Okay. But so far we have tackled, or we have taken a look at the pointwise intersecting case for the finite general group. But we could lose this condition a little bit more, which leads us to the t-space intersecting sets. Okay, what is the t-space intersecting set? Again, an example. Here I would like to indicate the two-dimensional subspace, which is spanned by blue and orange by the 4 colors that you see on the right-hand side. So now taking, in this example, 2 rows, we now see that they are equal on a 2 space. So the image of this 2 space spanned by blue and orange is again the 2 space spanned by blue and orange. And that would apply for any combination that I would take here. So this gives us a 2-space intersecting set. So in general, a subset of the finite general group is t-space intersecting if taking any 2 elements of the subset, so any 2 matrices, we find a t-space on which they're equal. And this example here is again a special one because it is indeed a subset. It is a subset of the stabilizer of a 2-space. And again, any coset of the stabilizer of a t-space is in fact t-space intersecting, and its size is given by the product that you see here. So the question that may arise again is whether this gives us again an upper bound on the size of t-space intersecting sets, and whether they are the only t-space intersecting sets of maximal size. Okay. So what was known is that for t equal to 1, a 1-space intersecting set in the finite general group is bounded by the size of a stabilizer of a 1-space. Okay, but here is a comment. This result was in fact stated for the projective general group. But since I want to stick with the finite general run for this talk, I wrote it down this way. So if you prefer the projective general group, just divide everything by q minus 1. Okay. So we came to the following result, namely having a t-space intersecting set in the finite general group. If n is sufficiently large compared to t, then the size of this t-space intersecting set is bounded by the size of a stabilizer of a t-space. And in case of equality, the characteristic vector of this intersecting set is spanned by the characteristic vectors of cosets of stabilizers of t-spaces. Okay, but the question that is unanswered so far is whether the cosets of the stabilizers of t-spaces also give us the only t-space intersecting set of maximal size. Okay, but like it was in the pointwise intersecting case, the answer to this question is again no, and the reason is basically the same. So having a t-space intersecting set, then the set consisting of all transpose matrices is t-space intersecting again. Yes, okay, sorry, yes. But what holds indeed is, so having okay, right. So I wanted to mention what was already known, namely having a one-space intersecting set of maximal size. Then it is either a coset of the stabilizer of a one space or a coset of the stabilizer of an n-1 space. Right. So in addition, having a one space, a coset of the stabilizer of one space and taking all transpose matrices of it, then we get a stabilizer of an n-1 space. So which led us to the following conjecture, namely having a t-space intersecting set of maximal size. And if n is sufficiently large compared to t, then this set, or the set consisting of all transpose matrices, is a coset of the stabilizer of a t-space. Okay. So these were the results or the conjectures for the finite general group. But how do we attack this problem now in order to prove this? So we will focus again on the pointwise intersecting case. Okay. What we want to do again is we're going to construct a graph such that our t-intersecting set is an independent set within the graph. We want to apply and we want to apply the weighted version of the HOFFMAN bound. Okay. So what we first of all need is that we have to recall what the conjugacy classes in the finite general group are. So for this, they are indexed by partition valued functions such that a condition corresponding on the degree of the irreducible characters and the partition size hold. So in correspondence term. Okay, as an example, let us take a look at the following partition valued functions. So here we have our mu only supported on an irreducible polynomial of degree 2 and on the irreducible polynomial x-1, where the partition corresponding to f2 is n2, 1, and the one corresponding to x-1 is 2. So visualizing this and taking the green box to be the companion matrix of f2, we get the following representative of the conjugacy class corresponding to our mu. So here we see that we repeat the companion matrix of f2, first of all, 2 times, which corresponds to the 2 in this partition. And since there is a 2 or a number larger than 1, we will add in the identity matrix of appropriate size. And then we have another one in the partition, so we add another box which is a companion matrix of f2. And we will do the same for the polynomial x-1. So here the companion matrix is just a 1 times 1 matrix. We repeat it twice due to the partition up here. And then we add the identity matrix of appropriate size, which is just the 1 times 1 matrix. Okay. But not only the conjugacy classes are indexed this way, but the irreducible characters of the finite general group as well. Okay. Well. Right, as I just mentioned, we wanted to apply the weighted version of the HOFFMAN bound. So we have to get an association scheme that we want to work with. And that we want to pick is the following. So we take our vertices are again the elements of the finite general group. And the adjacency matrices are given by the following. So now they're indexed by the partition valued functions, since they correspond to some conjugacy classes. But here we now take the union of 2 conjugacy classes, so differently from the symmetric group case. And the reason is basically because in the finite general group, whenever x-1y is contained within a conjugacy class, it is ensured that it also holds that y inverse x lies in the same conjugacy class. So in order to get our undirected graph for the association scheme we want to look at, we have to take the union of the conjugacy class and its inverse. Okay, so this gives us, in fact, an association scheme, and we can write the eigenvalues down again in terms of the irreducible characters, where they now look a little bit different, because they are consisting of some psi up here, which is just either the irreducible character itself or the sum of two of these irreducible characters. So in order that we get only real value characters that occur here. Okay. So thinking about our weighted linear combination up here, our eigenvalues corresponding to these lambdas now look like this. So we again have a weighted sum over some characters here and another quotient there. So what we again have to make sure is which characters do we take? So to which characters should our minimal eigenvalue of this weighted linear combination should correspond? And for this, we will again make use of the following, namely the sum of these vector spaces, where we just take certain lambdas, is spanned by the characteristic vectors of t cosets. So for our extremal case, we have to make sure that our characteristic vector of our intersecting set lies in or is spanned by the characteristic vectors of t cosets. So we have to make sure that we will be contained in this in the eigenspaces corresponding to these lambda. So we want to have that our minimal eigenvalue is only corresponding to these lambda where the condition of the sum holds. So that's how we pick our lambdas. Okay, and now coming to our conjugacy classes. As a recall, whenever we have a matrix that fixes the t-space pointwise, it is equivalent to the fact that the rank of this matrix minus the identity matrix is at most n minus t. So keep that in mind when we now take a look at the following examples. So here we see just sum of the conjugacy classes of the finite general group of 4 times 4 matrices over F2. And whenever you now here see a box with F and an integer in it, this means in this case, for example, this is the companion matrix of the irreducible character, irreducible polynomial of degree 4, here of degree 5, and so on. So having the conjugacy class corresponding to such a matrix, this does not fix any non-zero vector. Okay, and that is due to the fact up here and recalling how the companion matrix looks like. Taking the irreducible polynomial of degree 3 together with the one coming from x minus 1, we now see that this matrix indeed fixes a non-zero vector. So we could proceed in this manner. And what we now see is that now the orange mark conjugacy classes do not fix 2 linearly independent vectors of f2 to the power of 3. So for arbitrary n and t, what we could take is we could take the conjugacy classes whose representatives are of the following form. So we have a block, so a companion matrix corresponding to an irreducible polynomial of degree at least n minus t. But have to pay a little bit more attention whenever we have ones occurring on the diagonal for all t, for the completely t place that we still have to put, because this one would fix t linearly independent vectors. Okay, so this will be our conjugacy class that we want to take for our weighted linear combination. So now assuming that there exist these weights, okay, such that these were our minimal eigenvalues of the weighted linear combination, so the one on the right and left hand side, and we just take these lambdas that we were speaking about the slide before, such that our minimal eigenvalue looks like this, and it only corresponds to the lambdas that we just picked a few slides before. And now applying the weighted version of the HOFFMAN bound give us our desired upper bound on the size of t-intersecting sets of the finite general linear group. And in case of equality, the characteristic vector is spanned by the characteristic vectors of t cosets. And that is because due to our condition that we just took for these lambdas. Okay. Right. And now the question is again, how do we explain if these weights exist? And well, so what we have in this case is, again, we interpret this one here as a system of linear equations. So we have to focus on the matrix coming from these characters here. Okay, and as you may have seen, the size is now really a quadratic one. So we have equal rows and columns. So let us take a look at an example. So in the case of the finite general group of 5 times 5 matrices over F2, we have to take a look at the matrix coming from these characters and these conjugacy classes. So these are the one that we just picked. And we would have to explain that this matrix is in fact, so this matrix coming from this table is in fact invertible, which would give us the existence of our weights. Okay. Okay, so for the following slide, just let me tell you that we can make the following correspondence. So we could associate some of these characters to some conjugacy classes. So whenever we see here a 3 in the partition corresponding to x minus 1, then we associate them with an irreducible polynomial of degree 3. So we get these boxes up here that I just marked here, and they will be important for the next slide. So now, using the representation theory of the finite general linear group, would give us the following, namely, so this is again the matrix coming from the table we just saw on the slide before. So there exists a matrix which is lower triangular and invertible, such that multiplied to this little corner of the character table, we get such a matrix. So a block upper triangular matrix, where now you see why I marked these different blocks. So they correspond to the association we just marked on the slide before. Okay, but differently from the symmetric group setting, we now have to do a little bit more work because it is not upper triangular one, but just a block upper triangular matrix. So we still have to explain why this little 3 times 3 matrix is in fact invertible. And we can do this by using a little bit more representation theory, namely, this matrix is again a product of 2 invertible matrices. Though this one is something similar to the one here up here, but this matrix here is in fact the complete character table of 2 times 2 matrices over F2. And taking a complete character table, it is known that this one is an invertible matrix. That comes from the representation theory. Okay, so we conclude that this matrix we started with is in fact a product of 2 invertible matrices, which gives us the existence of our weights we wanted to. Okay, but as you may have seen, I just put up an example for Q2 equal to 2. So in general, with Q greater than 2, it gets way more complicated, and we have to pay more attention which conjugacy class we pick and so on. But this is just the idea, what we wanted to do. Okay. Yes, so right, where do the matrices come from? So as I just mentioned, this comes from the representation theory of the finite general linear group. And in order to explain this a little bit more, I would just introduce a notion, but do not want to go into too much detail. So having 2 characters of 2 different finite general linear groups, so 2 different sizes, so two little finite general linear groups, we can construct a character coming from the bigger finite general linear group. So having one of GLKQ and GLRQ, we can just take the product of these characters, which then give us a character of the finite general group of K plus L matrices. Okay, so this is just the notion of this symbol up here. Okay, well, due to James, one can construct such called primary characters, which are only supported on one irreducible polynomial, which maps to one partition, and they are the product of so-called cuspidal characters. So these one can be constructed. And the nice property of them is that they decompose in the following way. So here we see our Koska numbers again. Okay, and these one are the irreducible characters then. Yes, and now since we can construct these psi for every f and every partition mu, this also gives us the irreducible characters, so at least for the primary ones. But now taking the primary characters, we can define irreducible characters of our bigger finite general groups, which is just the product of the primary ones. And now we are nearly done. We still need these xi's for the bigger finite general groups. So we also take the product of the primary ones. Okay, and now the nice property of these characters is basically that the following holds. So we have again a matrix product. So this is again the matrix notation, and the matrix from the slide before on the left-hand side then is a block diagonal matrix, which comes from Koska numbers. Then we have our irreducible characters, and they are equal to these xi's that can be, as I just mentioned, constructed. Okay. So this was the comment on the representation theory of the finite general group. Well, okay, and now I still wanted to comment shortly on the results for the extremal case. So yes, as I mentioned a few slides before, the upper bound and the conjecture was proved in a different setting, so namely for t-1 intersection free sets. But what is a t-1 intersection free set? Well, having a subset and then just taking all elements on which any two of these elements agree. So we is not equal to q to the power of t-1. Okay, so this gives us that any t-intersecting set is also t-1 intersection free. And indeed, it was proved by Ellis-Kinner and Lifshitz that having a t-1 intersection free set, and if n is sufficiently large compared to t, then the size of this t-1 intersection free set is bounded by the size of a t coset. And in case of equality, the set or the set consisting of all transposed matrices is a t coset. Okay, so they tackled a more general setting. Okay. Yes, and I would like to close this talk with just an overview on the upper bounds that we just saw on the slides before. So the left column corresponds to the bounds for the symmetric group, and the right one for the finite general one. Yes, so thank you.
Thank you for the talk. Any question for Alena?
Yeah, I guess I have a couple. Let's see. So were you able to get any results on T cross intersecting?
Yes, yes, indeed. But it's so
I figured you would get that for free, just using the proof technique that you described.
Yes, it comes for free from where is it? I think I put it somewhere down. So from this condition up here. Right. So it's also in the paper. So it comes exactly for free. Yes. Yeah.
Yeah, so I guess another question if nobody has any. So with the finite general linear group, there's just like there's a ton of these, or maybe not a ton, but so a lot of these different Gelfand pairs that you can consider. So the one that you're considering would be GLNQ cross GLNQ modding out by the diagonal of GLNQ. But there's there's a bunch of other group subgroup pairs you can consider where you have like an association scheme and multiplicity freeness and all that. And also there's lots of I guess sub-association schemes you can consider with the finite general linear group, and this gets into things like Gelfand-Grave representations and things like that. But have you considered looking at any, or is there any that you have your eye on maybe, or
not right now.
Okay.
So not for the intersecting sets, no.
Nice.